what do the standing wave harmonics with fixed endpoints look like? Another way of maybe phrasing this question is to say, if I had a medium with fixed endpoints and I want to put a standing wave in there, how many different ways could I do that? Maybe starting with the least complicated. So if I kind of start with a point here that represents a fixed endpoint, and here's another one, maybe the simplest thing I could do is have a standing wave that just has a single antinode halfway in between those two. And so in other words, that standing wave would kind of oscillate between these two curves. And then maybe the next thing I could do is, if I said let's make it a little bit more complicated, is let me draw one that has two antinodes instead of just one. And that's really the n equals 2 that we already saw on the key concepts page. I decided not to draw my fixed endpoint to start with there because I have trouble hitting the target when I do that. But now that I've got that part, maybe I can fit in the other extreme of the standing wave motion there. It's not perfect. But this would be like the next one up, and so on and so forth. Let me try for one more here. If we get 3 antinodes perhaps, so there's one antinode, then I'm going through a node, I'm going to hit another antinode, going through another node now. Here's the third antinode, and then I want to get to the other fixed endpoint. And so that gives me another picture of a possible wave. And when I do it this way, where I'm just adding, oops, kind of screwed up that last part there. When I'm just adding antinodes, I wind up getting the full harmonics that are possible. So that really is the standing wave harmonics. So let's go ahead and look at what's in the picture here. I think it'll be much nicer looking. And it shows, you can see the first 3 that I just tried to sketch. They're a little bit better. And there are some labels here, like this first one. This is actually n equals 1 and is the fundamental but first harmonic. And when we say n equals 1, that is the harmonic number, but it's also the fundamental frequency. And then there's one here that's labeled as the first overtone. So that's this is kind of 2 maybe competing sets of terminology, harmonics versus overtones. And something that's a little weird is that when you're at first overtone, it's second harmonic. And again, n is not the overtone number, but is the harmonic number. So this is n equals 2, as we saw in the key concept slide. But then we keep adding, we get n equals 3 and n equals 4 and so on. And that's with the formula we have in the key concept slide. That tells us what the wavelength is for each of these. And we can maybe check that out real quick here, because that wavelength formula was lambda is equal to 2L divided by n, where L is the length of the medium between the two fixed endpoints. So for the fundamental first harmonic, n equals 1, the wavelength, I think we're only seeing half a wavelength here. And so that means the full wavelength is actually double the length L. And the formula would say 2L over 1, so that's 2 times L. For n equals 2, though, n would be equal to 2, right? So that means that lambda is equal to 2L over 2, which is really just L. And that aligns with this picture here where you see one whole wavelength between the two fixed endpoints. If you look at the third harmonic, which is n is equal to 3, we'd have 2L over 3. So that means lambda is equal to 2/3 L, but it also means that L is equal to 3/2 times lambda. And one way of interpreting that is you could say that we see here 1.5 wavelengths, right? Because this is a full wavelength right here, even though it's not really crest to crest, but you can see that's a full wavelength. And then there's another half right there. So that aligns with the 2/3 you get in this formula when n is equal to 3, and so on and so forth.